The title here is a little bit of a mouthful. 3 approaches for printing traditionally metal parts. And so the main reason that I wanted to talk about this is because we get a lot of customers that come to us and they have these metal parts that they've been making out of metal for, a really long time. They've been in the business for 20, 30 years. And the first thing they want to do is start printing them out of metal. And, sometimes that's a good option, but a lot of the time we're able to push them towards, different approaches and things that may save them time or money. So that's kind of what we're going to talk about today. And before I go too deep into that, I'll just quickly introduce myself. My name is Bryce Babinick. I'm an additive manufacturing technician. I got a mechanical engineering degree in school and I worked with 3D printers a lot there. Built what turned into kind of a minor obsession with printers, so have quite a few going at home, got a little collection, fun little Etsy projects and things like that here and there. So was excited to take the job at MLC CAD Systems. We're a company that offers basically engineering, hardware and software implementation options. And so we'll do installations, we'll do tech support, different training, whether it's custom or just training on the machine. So we've been around for a long time with just SolidWorks and Mastercam. We're one of the world's biggest Mastercam resellers and definitely one of the top SolidWorks resellers. On the additive side, we've worked with Markforged for a long time. Markforged primarily does FDM or FFF printing. And so for those of you who aren't familiar, FDM is just the traditional one that everybody's pretty much seen. You've got melted plastic coming out of a nozzle, building a part up layer by layer. We recently started working with Formlabs, and Formlabs is big in the SLA world. So they've got resin printing. So you've got a liquid resin photopolymer that comes in and it's cured by a laser. And it, again, builds it up layer by layer into a part. And they also work with SLS printing, which is a powder in a vat. Again, uses a laser to melt it and builds your part up. It works really well for higher throughput. So pretty cool options across the range. And we do a lot of work in the manufacturing sort of industry. So we'll kind of dive into a little bit into each of those, but we'll look a lot at Markforged and some of the capabilities there. So the first thing that we do anytime we get one of these parts from a customer, we've got to ask them, all right, well, why is this thing metal? We need to revisit it. Usually there's a couple of reasons. If it could have been made from plastic, there's cheaper options out there. That's probably the route you would have gone. So we need to identify the specific attributes that made that part metal. And so these are a couple of the big ones. And when we're looking at this, you've got appearance, you've got surface hardness. Plastic may not be cutting it. You've got like abrasive forces that are cutting away. You've got some wear resistance that you may need, similar characteristics there. Whether it's threads, strength and stiffness, thermal and flame resistance. There's a lot of properties here that we may see that maybe aren't on this chart, but these are some of the biggest ones that we come across. So the first thing that we're going to look at here is using localized metal properties to meet some of these strength attributes or whatever physical characteristics that we need to by using, again, localized metal properties. So let's take a look at it with each one of these. We'll start with something easy. Threads is something that if you've been around 3D printing or any sort of plastic manufacturing, you've probably seen some of these options. But let's dive into it a little bit here. So yeah, the first option is probably the first one that would come to your head. You can just tap it. You can thread your bolt right into that 3D printed hole. You want to undersize it a little bit so you can actually get some purchase with your threads. If it's a little bit bigger, like say 1/2 inch or M12, you want to think about printing your threads, whether it's the male or female side. And this works really well with SLS printing and SLA, where you've got a little bit more strength between your layers. So again, this is a good option. It's quick and easy, but it's not always the best case because it's not necessarily the strongest option. You're working with plastic on plastic, so you can't use really high torque applications or pull out strength applications. And so for those, we tend to use heat set inserts. And so these are just, little brass inserts that you pick up. You use a soldering iron or some sort of heated device to melt them into your part. and add that thread in there. You can do this in any sort of plane or any sort of direction, and you get a really, really strong thread here. It works really well if you're doing repeated use with the threads. So if you're taking something apart, putting it back together, this is a really good option for you. If you're working with a part that has a lot of threads and it doesn't necessarily need that really, really high pull-out strength, the embedded hardware is really nice. So on the right-hand side for you guys, I forget, I'm all flipped around here. The right-hand side is going to be embedded hardware. So we've got a breadboard that we worked with for a CMM fixture where you're testing your parts, making sure it's as accurate as it can be. And so we had a lot of threads. We wanted a lot of mounting points. And so we did that just by using hex nuts. And you can do this with hex nuts or square nuts. You create a void in your part. You drop them in there. You continue the print. And it's going to add the rest of the print on top of it. And now you've got that thread captured inside of your part. So again, a really convenient option if you're using a lot of thread, because you can just drop them in there, continue the print, and you're good to go. So let's move on to something a little bit more serious. And for you guys in the back that work with the robotic grippers, this one's for you. In the picture you can see for wear resistance, you've got a robotic gripper that opens up and it's grabbing these pipe threads. And they tried printing this part out of plastic at first, and because it's threaded where that robotic gripper is grabbing, it was wearing away at that printed surface really quickly. So they came to us and they brought up metal. We want to print this thing out of metal. And it's a decent sized part. We could do it out of metal, but there's an easier way to get away with this. And so the way that we, push them to do it is just using dowel pins. You can use something really cheap and simple that you buy off the shelf and add it into, a regular composite printed part. And now you're able to get that wear resistance on this surface. And so if you're working with like a curved or cylindrical surface, the dowel pins work really well. If you've got a flat gripping surface or wear resistant surface, you can use machine keys and get away with the same thing there. But sometimes you need the entire surface. It's not just one contact point. Sometimes you need the entire thing to be a little bit more stiff or hard, whether it's for appearance or for actual mechanical properties. And so we've got another great option there. And it's one that's been around for a while, and it's just to electroplate your parts. And so people have been doing this with metal for a long time, and people have been doing it with plastic, but it's actually growing in popularity with 3D printing. And you get a couple of cool benefits out of it. One of the main ones is that you're still getting that lightweight printed core, but now on the outside, you've got however many layers of metal adhered to your part to give it that strength. So it's sort of like an exoskeleton for your part. And so Formlabs actually did some testing on this with their rigid 10K resin, and they saw over 250% increase in strength on a resin that's already really, really strong. So great option. And again, you got a strength to weight that can surpass even fiberglass. And in our bottom picture there, we've got one that a company that is in the aerospace industry works with. They work on these really, really high-end jets, and they try to make bezels for them. But one of the things that you have to worry about when you're in aerospace is whether or not your parts are flame retardant or flame proof, heat proof, whatever. So that brings us to our next one. And so when you think about it, obviously you don't want your plane on fire if you're in there. But the other part that you may not think about is you're trapped in that cabin with whatever's on fire. So you're breathing in whatever fumes and smoke and stuff is in there. And so that's why in aerospace, there's a lot of requirements around what materials go in and whether they're self-extinguishing or what kind of fumes they put out when they're on fire. And so the easiest way for us to get around this is just by using some pretty interesting material properties. And so that's why Ultim has been a really big thing, but Ultim's not the only thing out there. And so we've got a couple of options from Markforged, Ultim being one of them, but they also offer an Onyx FRA, which is just a nylon 6 with chopped carbon fiber in it. And this option is UL94V0 rated, which is a bunch of numbers that didn't mean much to me at first, but that just means that it's self-extinguishing within 10 seconds. And so now you've got a part that you don't have to worry about catching on fire, and it's approved for aerospace. The other side that you get out of both Ultim and Onyx FR is that it has traceability. And so, and again, in aerospace, you have to have traceability from when the material is manufactured all the way to when it became a part. And so Markforged offers that as well. So On the resin and Formlab side, we don't have as much to work with in the lot level traceability aspect, but we do have some different resins that have pretty impressive capabilities. So the high temp resin can go up to 500 degrees Fahrenheit. So really impressive if you're doing like welding fixtures or any sort of like work holdings. And on the powder side, if you need a lot of these parts, even the nylon 11 with carbon fiber has a pretty significant heat deflection temperature. So moving on to probably the biggest and most important one, the main reason that people make parts out of metal is going to be strength and stiffness. And so we've got in our picture here in the upper right is going to be this press brake. And this was from a CNC job shop company. They're making these really simple parts. They needed to press out these little tabs inside of the part. And it was a small job, and they didn't want to take it on initially because they didn't want to invest the money into tooling. It would have made the pieces overpriced, and they were going to turn them down. But we tried to work with them on how to manufacture the punch and die for these, and we were able to get away with a couple of cool tricks. Before I get into those tricks, we're going to look at just the base material properties because these are pretty impressive just by themselves. And so we've got a chart. This is just some of the various filaments and resins that are offered. And we're almost halfway to aluminum here, so pretty good for right off the bat, just your base material. And we're trying to remember this chart because we're going to take another look at it later on. But yeah, I just wanted to cover that. The base materials are pretty impressive by themselves. So moving on to how we solved the problem for the initial company there. And it's this first picture in the top left. So they actually just used some really simple sheet metal pieces embedded in the part, and it gave the printed part enough strength to be able to be used as this press brake. And they even got to use infill with it as well. So still lightweight, saved them a lot of money on material, and ended up working out really well for them. So some of the other things that you can get away with here are using just bolts for FDM or FFF printing to adhere your layers together. You don't have as much delamination. It creates this sort of stress cone and compresses the layers in sort of like a diamond shape like we're seeing there. But it doesn't stop with just those things. You can get as creative as you want here. And so we've got a bottle opener that we used a nickel for. We've used steel braided cable to add some tensile strength to our parts using just a soldering iron, pausing it, and melting that braided cable into it. You can get some pretty interesting effects using that. You can grab a wrench if you've got one around, or if you've got a coworker that's not using a cell phone, you can throw it into the middle of a part if you want. And make sure to use the pink plastic for that, so when they rip it open, they're really happy. So that's localized metal properties. There's a lot of really cool stuff you can get away with here, but not everything, not everybody has the time to sit there and embed wrenches or phones or whatever into your part. Sometimes you've got to have a little bit higher production than that. And sometimes you don't want to sit there and test your part, break it over and over again. And for that option, we've got metal strength through fiber reinforcement. And if you guys haven't heard of Markforged, this is really where they shine. And so that's what we're going to lean pretty heavily on in this section. And this is one of the reasons why. So this is a incredibly strong link that Markforged was able to just print using embedded continuous strands of carbon fiber, and it was able to withstand 22,000 pounds. So you can get away with some pretty impressive stuff when you use this correctly. Before I get into how it works, here's that chart again, and this is why we want to use fiber, because now we're above aluminum, we're almost double aluminum. This is why carbon fiber and fiberglass, any of that stuff is as popular as it is, because it has an incredibly high strength to weight. And so we really, really want to take advantage of that. And the way to do that, you can't just print something out of straight carbon fiber. And it's the same way that you wouldn't build a building out of just rebar. You need to have concrete. And so that's what we use our base materials for. So the way that Markforged gets away with that is they've got a dual nozzle system. And so the back nozzle will just lay down your plastic, your onyx, which is a nylon 6 with chopped carbon fiber. And now we've got another nozzle in there that's basically melting and ironing that fiber into your part. And so now you're taking full advantage of the fiber strength, and you're still having the exterior part of it as a just 3D printed plastic or composite. And one of the benefits that you get when you use this is you can sort of apply your fiber based on your loading conditions. So their slicer is really convenient. It's really easy to use. And there's a couple of different ways you can lay the fiber into the part. And so if you've got, using this motorcycle brake lever, if you've got the force coming in perpendicular to your XY plane or perpendicular to the bed, however you want to see that, you can lay your fiber isotropically, where it's just totally filling the layer. And when you do this, you want to think about it in sandwich panels. And it goes back to the whole beam bending. I don't know if you guys saw that in school, but when you have a force and it's bending a beam, you've got your highest tensile and compressive forces on the top and the bottom. And so that's where you want to add your fiber. So you leave fiber in the top, fiber in the bottom. You just print the rest of the part out of regular plastic or whatever composite you're working with. That way you're saving money, you're not using as much fiber, and it increases your print times a little bit. So great option with isotropic. But if your fiber is just coming parallel to the build plate or parallel to your part, you can just use concentric fiber to wrap it around the outside. And similarly, if you have bolt holes like these mounting holes here, we could wrap fiber just around the inner holes to reinforce those. So again, bolt holes or any sort of mounting surface, it works really well with. And another one of the benefits of using this system is you can actually now simulate your parts. So, before we've got a system where we're printing, we're breaking, we're testing over and over again. You've got this really iterative cycle, and we might still have that here. But with Markforged simulation, you can actually reduce that process, save yourself a lot of time, and again, a lot of money on your parts. And so you set up your loading conditions. It's really simple, really straightforward. You set up where this part is fixed by, you set up where the force is, you put your direction of the force, and you run it. And it will spit out whether it meets your factor of safety, whether it'll meet your deflection criteria, and you can fully scale it. You can let it give you an exaggerated curve of where the part is bending or breaking. And once you've met these requirements, you can even optimize the part. So you can come in there and you can ask the slicer to spit out what's the fastest way to make this part, what's the least expensive way to make this part, what's the strongest. So you get a lot of really cool options and a lot of variability there where you can play around with it. When you've used it correctly, so it's just another example, one of my favorite ones here. This is a company, they're in Europe, so these were their numbers that came with the slide. So we've got our US numbers here looking at this. But yeah, just a really cool part. This is a company that makes boat engines, and so they've got these giant pistons that they have to move around the shop. And before they were printing this part, they had to go get a crane to go get the part, to put it on the crane, and move everything around. People were hurting their backs trying to lift this big, giant piece of tooling. And so they were actually able to print it using the carbon fiber technology. And this thing could lift over 2,000 pounds, and it was actually CE certified to be used. So pretty impressive what you can get away with, really cool capabilities. And now they don't have to, again, go get a crane to bring the actual lifting arm over to use the crane to lift the piston. So saves them a lot of time, really cool application there. And again, saved them a lot of money on machining the tool as well. So that covers the first two. We've got metal on here as well. And there's a lot of metal here that you've probably seen for additive. Our technology is a little bit different, and it takes advantage of a couple of different systems. And we've got a couple of options there. So let's dive into those. On the Formlab side, if you need, if you have time basically to print and mold and create your part, then you can actually use just their castable wax resin. And so this is going to print, just like an SLA part, and you've got a liquid resin that's being cured, but it's actually made of wax. So you create your mold around this part, and then you bake that wax out, and now you've got a mold that's ready to go. You can pour in your metal and create your part. So really cool option. It's very affordable, but most of the time in the manufacturing world, we're working with the Markforged Metal X system. And the way that this works is we're still using metal powders like a lot of the companies here are, but our powder is wrapped in a binding agent, so it's just like a wax and plastic. And now we've got it on a filament spool that we're able to print just with FDM. You can have it in an office. It's very safe. It doesn't have the explosive and health hazards of powder, so we don't have to have a dedicated room for this and dedicated PPE. So it's a 3-step process. You've got it in the printer, you print it. You've got to get rid of some of that debinder in basically an industrial degreaser. and then we throw it in a sintering oven, and that bakes all those particles together, and you've then got a 97% dense part. It's pretty close to what you get out of cast or like a machined piece. And so you get a couple of interesting benefits out of this. So one of them we touched base on already, which is that you've got no metal powder hazard. So you've got it just sitting in a build chamber. You take it off of your build plate and you drop it into the wash. So really easy to work with. But the other benefit, again, for my robotic gripper guys, is that you get an infill with these still. So you've got lightweight metal parts that you can have higher cycle times on, because it's not just some big heavy piece of metal floating around out there. And you can play around with this. You can increase your walls or decrease them based on if you're going to do some post-processing or machining with them. So fun options there. And then one of the kind of unique things that you see out of this process is that between printing and sintering, you can actually handle this part just like clay or plastic. So this was a blade that I worked on, and I was actually able to sand it and get it a little bit smoother while it was in the green state between printing and sintering. And then we sintered it, and it was much smoother where I wasn't working with metal and a grinder and a polisher and all that stuff. So really cool project. But yeah, again, after it's sintered, it's just like any other cast or machined part. And there's a lot of people that can talk more to that. So I won't dive too much into the post-processing on that side. So that's all three of ours covered. There is a small bonus option here, and it's just that you're not limited to any one of these options. You can combine them. And so that's what I did with the knife project here. I've got, the handle doesn't need to be metal, so I just filled it full of carbon fiber. I've got square nuts embedded into that part, and those square nuts are now wrapped in fiber, so they're even stronger. They have a higher turnout strength. I've got a dowel pin that works as the blade stop, because again, it's a simple part. I don't need to print that. And then of course with the blade and some of the other pieces, we've got those printed out of metal. So really cool to use all three together, and there's a lot that you can achieve by taking advantage of that. So cool. That's all we got for you guys today. Is there any questions or anything? All right. Thank you guys. Appreciate it.